Hello, this is lecture 4, section 2.2, graphs of linear functions. All right, let's start with a definition. What is an intercept? An intercept is a point where a graph crosses one of the axes. The x-intercept is where a graph crosses the x-axis. The y-intercept is where the graph crosses the y-axis. Excuse me. So linear functions are, one way to graph linear functions is by finding the intersects, plotting those points, and then just connecting them. So in these examples here, let's see if we can graph the function using its intercepts. So in order to do that, we'll need to find them first. So to find the y-intercept, all right, to find, let's write that down up here. To find the y-intercept, you want to let x equal 0 and solve for y. All right, so for this equation here, if x is 0, what we're really looking for is f of 0, right? And that's going to be 2 times 0 minus 4. 0 minus 4 or negative 4, right? So the the y-intercept is going to occur down here on the y-axis at negative 4. The coordinates of that point are going to be 0, negative 4, right? So there's our y-intercept. And why do we let x equal to 0? To find the y-intercept? Well, all the points on the y-axis have an x-coordinate of 0. So if we let x equal 0, we're going to find where this function will cross the y-axis. All right, so the coordinates of that point are 0, negative 4. All right, to find the, so that was our y-intercept. To find the x-intercept, we'll write that up here. To find the x-intercept, we want to let y equal 0 and solve for x. All right, so for this equation here, where would y be 0? Maybe we'll do that down here. We'll say 0 equals 2x minus 4. Remember, f of x is just function notation for the y value, right? Now we'll just solve for x. Right? So if we add 4 to both sides, 4 will equal 2x, and then divide both sides by 2. Dividing both sides by 2, we see that x equals 2. Right? So the x-intercept is going to occur here when x equals 2, or the coordinates of that point are going to be 2, 0. Okay, we only need 2 points to graph any line since we have these 2. All we need to do is connect them, and we have the graph. We have the graph of the line. We have the graph that is the line for f of x. Okay. Should we do one more? Our y-intercept, of course, is for this part B is going to be g of 0. So what is g of 0? It's going to be 3 minus 2 thirds times 0, or simply 3. The coordinates, then, of that y-intercept are going to be 0, 3. That point will be right there. Okay, and then to find the x-intercept, let y equal 0. So 0 equals 3 minus 2 thirds x, all for x. Let's subtract that 3 from both sides. So negative 3 then equals negative 2 thirds x. And if we multiply both sides by negative 3 halves, we'll just have x left, x remaining on one side. Okay, so negative 3 halves. Let's look at this. 3's will divide The 2's will divide out, and the 2 negatives become positive. So what do we have over here then? We have negative 3 times negative 3 or positive 9 halves is equal to x. So the 9 halves is about, or it actually is 4.5. 4.5, the x-axis occurs right here, and there's our 2 points. Okay? And there's the graph of our line for g of x. All right. There are other ways to graph lines. If we have a function, right, it's in its standard linear form. Remember, y equals mx plus b. So that would be function form. We could say that f of x, mx plus b. In this situation, we can see that b, recall from the previous section, b is y-intercept, and m is the slope. So we can think of m as rise over run, our slope, or our rate of change. Our b is our y-intercept. Well, if we look here at part A here, f of x equals 2x 3, it is in the standard form. So we can see that the slope is 2, and we could write 2 as 2 over 1 if we want to think rise over 1. We can see that the y-intercept, or the b, the y-intercept is negative 3. So we can graph using this standard form. We know the y-intercept is negative 3, so we know this point is on the graph. And then if we just count rise over run from this point to a second point, we'll have 2 points that we can connect for the graph of that line. Right, so 2 over 1, they're both positive, so we'll go up 2 and to the right 1. We might even do it again, or a few times if we wanted several dots to connect. And there we can see is the graph of that linear function, 2x minus 3. Okay? Try it one more time. The y-intercept here is 1. So there's 1 point that's on that line. The slope is negative 3/4. Now negative 3/4 can be thought of as negative 3 over 4 or 3 over negative 4. It really does not matter. So if I start at this y-intercept and I count out rise over run, let's see, if I use the first, let's use the first version of it. The rise is negative 3, so instead of up 3, I'm going to go down 3. 1, 2, 3. And then the run is positive 4, so I'll go to the right 4. 1, 2, 3, 4. And there's a second point that I can use. Now I could have used the second version of this as well. I could have started here and done a positive 3 for the rise. That would be up 3. But then I would have a negative 4 for the run, so I would have to go left 4. 1, 2, 3. 1, 2, 3, 4. So that point would then be on the line. Doesn't matter which version I use. These are all points that are on that same line. Okay, graphs of linear functions. A third way that we could graph a linear function is using transformations. If we look at A here, negative x plus 3, what transformations do we see occurring from the toolkit function? Which toolkit function are we using here, right? F of x equals negative x plus 3. Well, when we look at the toolkit functions, we're going to be using the identity function because that's the linear function, right, that has an x in it. No, the constant function, but we have an x here, so we don't want that. We want the identity function. Okay, so what's happening? The identity function, without any transformations, would look like this. There's our identity function. No transformations. What transformations are occurring here? It looks like we have 2 of them, right? We have 2 of them. This negative here tells us that there's going to be a reflection, right? Are we reflecting across the y-axis, a horizontal reflection, or are we reflecting across the x-axis, a vertical reflection? Recall that vertical reflections make the whole function negative, right? This f of x, as it's presented here, negative x plus 3, only the x is becoming negative. And with linear functions, it honestly doesn't matter a whole lot. It doesn't matter a whole lot, but it's best because you can do it either way. It's best to start with what is most apparent, right? So I would say that this is going to be a horizontal reflection. And then what else is happening? Let's write that down. The first transformation, horizontal reflection. The second transformation looks like a vertical shift, right? I might say that's shift up 3. Okay, so the horizontal transformation. Now let's put our transformed graph in there. The horizontal transformation is going to take each point on this graph and reflect it over the y-axis. So if we reflect this point here, reflect it over, if it's 2 to the right, it's going to become 2 to the left. But we also have this vertical shift up 3, so I'll need to move it up 3. So there's a point that's on that line. Take some other point and transform it. How about the origin? When I reflect that horizontally, nothing happens, right? But I do want to move it up 3. I move it up 3, I get here, and then I can see that all I really need is 2 points here, right? There's the graph of my reflected line, or f of x. Okay. Original line was from my toolkit functions. That's the identity function, y equals x. Okay. Now, if I wanted to treat this as a vertical reflection, it would have had to have been written differently, right? It would have been a different equation even, because I would have had to have had parentheses around this, which would, of course, made the 3 being shift down 3. All right, look at g of x. What's happening here? 2 transformations again. It looks like, look at this, the x is being multiplied by 1/3. So what do I have there? First of all, I have a horizontal stretch, right, by 3. Just to review, why is that a horizontal stretch by 3? It's horizontal because it's only happening to the x, to the input. And it's a stretch because we are either stretching or shrinking by 1 over the constant. So 1 over 1/3 is going to be 3. So that's the first thing that's happening. The second thing that's happening is what? Shift up 2. All right. So the identity function before transformations, y equal x, is going to look like this. And there's our identity function. Now, after the transformations, let's just transform some points. Horizontal stretch by 3. That means we're going to take a point on this line and multiply it by 3. Well, let's see. Let's take this point here. When x is, and we're horizontally stretching, so when x is on the y, so we want to multiply the x by 3. 1 times 3 is 3, so this point would then move to here. But we then have to do the second transformation, which shifts it up 2. We end up right there. Interesting. Okay, let's see. What happens with the origin? Well, when we multiply it by 3, when we multiply x by 3, nothing happens because it's 0. But we do still have to shift it up 2, so it comes up to here. Right? Should we do another point? How about -1? When x is -1. Multiply -1 by 3, and we get to -3. That's over here. Then shift it up 2. And go there, right? So there's the graph. There's the graph of the line 1/3 x plus 2 using transformations. Now, would we ever really do that? We probably wouldn't. We'd probably go for the easiest way, right? I like when it's in this form, it's easy to start with the y-intercept and then do rise over run on the slope to find your second point. Anyway, very nice review of transformations, however. All right, horizontal and vertical lines are special. Look at this line A here, x equals 3. So it's telling me that x equals 3, always, right? Do we even care what y is? Y is not mentioned at all in this equation. So x equals 3 here on the x-axis, but x also equals 3 here, here. In fact, everywhere on this vertical line, x equals 3. Okay, the x coordinates of every point on that line are 3. And here's 3 points, coordinates 3 points on that line. The x coordinate is always going to be 3. All right, compare that to B over here that says f of x equals negative 2. F of x, of course, is just function notation for y. Right? So here we're saying y is negative 2. Well, where is that on the y-axis? Right here. Y is negative 2 and x is 0. But y is always negative 2. We don't even care what x is. This is the constant function from the toolkit functions, right? Y is negative 2 here, here. In fact, everywhere on this horizontal line, y is going to be equal to negative 2. We do not care at all about x coordinates because it doesn't matter. It's just the identity function in toolkit functions. Here's the, from our toolkit functions lecture, here's the identity, I'm sorry, I'm saying identity, I meant constant. This is the constant function from toolkit functions. Here is f of x equals 2. This one here, of course, is f of x equals negative 2. All right, a way to help remember horizontal and vertical lines is a little acronym. If you like acronyms, I don't tend to use them much, but someone showed me this once, and so I thought I'd share it with you. VUX-HOI is an acronym that can be used to remember that vertical lines, that's the V, have an undefined slope, and the equation is x equals a, some constant. All right? And horizontal lines, there's your H, have a slope of 0, there's your O, and their equations are in the form y equals some constant. Right? So VUX, vertical, undefined slope, x equal a constant. HOI, horizontal line, 0 slope, y equal a constant. Okay, let's talk about that slope for a minute. A vertical line has an undefined slope. Why would that be? Well, let's take a look at this particular vertical line that I just drew. We'll say the coordinates of this point are 3, 0. The coordinates of this point we'll say are 3, negative 2. And then we'll also put maybe 3, 2 on there. Okay, just the coordinates of 3 points that are on this vertical line. If I were to calculate the slope of that line, right, to go from one point to the other, there would be a change in the y's, but no change in the x's. Right? And recall that slope is the change in the y's over the change in the x's. Well, say I want to go from the lowest point to the top point, the change in the y's might be a negative 2 minus 2. The change in the x's is going to be a 3 minus 3, so it end up being negative 4 over 0. And we, of course, cannot divide by 0. Cannot do that. No division by 0. That's why we have to say the slope here is undefined. On the horizontal lines, we say the slope equals 0. Well, by the same thought process, if I have a horizontal line here at, let's just say that's at y equal 2, right? Coordinates of some points on that line. We may have negative 2, 2. We may have 1, 2. Those are 2 points on that line. Well, if I were to calculate that slope using the formula, change in the y's, or y2 minus y1, over the change in the x's, x2 minus x1, what would I have? In the numerator, I'd have 2 minus 2. Okay, down the denominator, I have 1 minus a negative 2. Or 1 plus 2, that's 3. So that simplifies to 0 over 3. And of course, we can divide 0 by 3. It's just going to, the answer is just going to be 0. And so on any horizontal line, it really doesn't matter what the horizontal line is or which points we're choosing. The difference between the y coordinates is always going to be 0. So we will always be dividing something into 0, and so the slope will always be 0. All right, just a little bit of review on horizontal and vertical lines. Right? And the last, I think this might be the last thing we talk about in this lecture, is parallel and perpendicular lines. All right, recall that parallel lines have the same slope, right? Or they might both be vertical if their slope is undefined. Sometimes we'll say the slope of line 1 equals the slope of line 2, a shorthand way of noting that parallel lines have the same slope. Parallel lines, of course, do not intersect. If we were to draw parallel lines, they look like a railroad track. They look like that. Those are parallel lines. Compare that with perpendicular lines. Perpendicular lines do intersect. In fact, they intersect at a 90-degree angle. So here's an example. Pretend that that's a right angle there. Here's an example of perpendicular lines. Now these slopes of these two lines are opposite reciprocals of each other, right? Opposite just means they have opposite signs. Look, the slope of one is positive, the slope of the other is negative. Reciprocals just means when I multiply them together, it will equal 1. It will equal 1 or negative 1. So let's say the slope of, if this is L1, we might say line 1. Let's say, for example, that its slope is 2. Okay, if these are perpendicular, line 2, this other line over here, its slope would have to be the opposite reciprocal. So we have the opposite sign, it's going to be negative, and it'll be the reciprocal of that. So it'd be negative 1/2, because 2 times 1/2 equals 1. Okay, opposite reciprocals. All right, let's look at some examples. Say we want to find the equation of the line that's parallel to this given function f of x that passes through the point 6, -3. All right, well, if it's parallel, that means the slopes will be the same, right? M1 equals M2. What is the slope of this first line? Looks like it's negative 1/2. These aren't necessarily written in the right order. Doesn't really matter, though. I could write this as negative 1/2 x plus 2, and it's still the same exact function, right? If I change the order of the terms, as long as I keep their sign. So it looks to me like the slope of this line is negative 1/2. That means that the slope of the second line is also negative 1/2. All right, so I can almost write the equation. Let's say the equation that we're going to find, we'll call it g of x. All right, I know the slope, so I know it's going to be negative 1/2 x, but I do not know what the y-intercept is yet. How might I find that y-intercept? Well, I know that this line passes through this point here, right? It has, for its x-coordinate 6, so x1 might be 6. For its y-coordinate, -3. Okay, and remember, function notation is just the same as y. So I could plug these x and y values in here and solve for b. I could say -3 is equal to negative 1/2 times 6 plus b, and solve for b. Okay, well, solving, let's see, negative 1/2 times 6 is -3. So we have -3 equals -3 plus b. If I add 3 to both sides, I see that b is actually 0 on this particular parallel line. So what is g of x going to be? It'd be negative 1/2 x plus 0, or that's kind of silly, right? We would just say g of x equals negative 1/2 x. Okay? Let's try it again. If we have, let's see if we can, not again, but let's see if we can find the perpendicular line. Let's see if we can find the line that's perpendicular to that function. Okay, now perpendicular lines have a different relationship, right? The slopes are opposite reciprocals, right? Slopes are opposite reciprocals. They have opposite signs. One will be positive, and when we multiply them together, reciprocals, when we multiply them together, how do you spell reciprocal? They're opposite reciprocals. When we multiply them together, they will equal 1. All right. Well, if the slope of my given line, or my M1, is negative 1/2, right? The slope of the line that I'm looking for, maybe call it h of x, slope of the line that I'm looking for, my M2 is going to have to be what? Well, it's going to be positive, right? Because they have the opposite sign. And what would I multiply 1/2 by to get 1? 2. So the slope of my second line is going to be 2. Right? An easy way to think about finding the opposite reciprocal, it's negative 1 over M1. Change the sign, whatever it is, and then divide it by M1 or flip it. That's the same thing. If you have a fraction, it's flip it. Okay, so h of x then is going to be equal to 2x plus b, okay, some y-intercept that I don't know, but I do know an x and a y coordinate of points that make this equation true. This ordered pair satisfies this equation of the line, right? Or when I graph it, these points are on the line. So I make that substitution, and I can say that negative 3 is equal to 2 times my x, right? That's my 6, plus b. Right, so negative 3 is equal to 12 plus b. When I subtract 12 from both sides, I see that the b is equal to negative 15. Now I can write my function. H of x is going to be 2x minus 15. Okay? This should feel like review. You certainly learned this in your last class, your previous class, your algebra class. One last concept in this lecture, let's talk about the intersection of lines. Okay, when lines intersect, let me just draw 2 lines. Look, when they intersect at a point. There's the point that they intersect at. Now it has some x-coordinate and some y-coordinate, but they're going to be exactly the same for both lines. Right? So what does that tell us? That tells us that where 2 lines intersect, the equations are going to be equal to each other. Right at this point, the 2 lines are equal, right? So if we set these 2 equations equal to each other, if we say m of x equals n of x, as I do at that point, y coordinates are certainly equal, we can then take the formula for those functions, 2x plus 3, and say that that's equal to negative x minus 5. Solving for x will give us the x-coordinate at that point where they intersect. All right, so let's go ahead and do that. We'll just go ahead and add an x to both sides, and subtract a 3 from both sides. So 2x plus x is 3x. That'll be equal to negative 8 minus 3. I'm sorry, negative 5 minus 3, which is negative 8. And then we'll just divide both sides by 3. So the x-coordinate at that point is going to be negative 8/3. Okay, negative 8/3. And how do we find the y-coordinate? Just plug that negative 8/3 into any of these equations, right? Let's see, I'll use, it doesn't matter, none of them are going to work well. Let's use the n of x. Let's find n of negative 8/3. N of negative 8/3 is going to be negative times negative 8/3 minus 5, or what is that, 8/3 minus 5. Well, to do that subtraction, I should probably rewrite 5 in thirds. So we'll multiply that 5 by 3 over 3. So h of negative 8/3 then would be 8 minus 5 times 3, 15/3, or negative 7/3. Right? So the point where these 2 lines intersect has an x-coordinate of negative 8/3 and a y-coordinate of negative 7/3. By the way, if I plug this negative 8/3 into m of x instead of n, will I get the same value? Yes, I will, because that's where they intersect. Just to prove it, let's do it. That was n, that's supposed to be an n, not an h, n of negative 8/3. Over here, let's find m of negative 8/3. Okay, m of negative 8/3, there's m. That's going to be 2 times negative 8/3 plus 3, or negative 16/3 plus 3. Rewrite 3 as thirds. We'd have to multiply by 3 over 3. So this is then going to be negative 16/3 plus 9/3, which of course is negative 7/3. All right, that ends the lecture for section 2.2.